Hello everyone, my name is Bharadwaj of ECE. I am here to represent the topic tensor network Kalman filter for LTI systems of signal systems. Introduction to tensor network Kalman filters for TI systems. The tensor network Kalman filter is a powerful tool for estimating the state of a system based on noisy measurements. Let the LTI systems refer to systems that are characterized by tensor interactions such as quantum systems or complex physical systems. These presentations will provide an overview of the tensor network Kalman filter and its applications in TI systems. And you can see the Kalman filter algorithms in the battery model in the picture. What is Kalman filter? The Kalman filter is a recursive algorithm used to estimate the state of a linear dynamical system. It combines measurements and predictions to provide the best estimate of the system's current state. Kalman filter is widely used in various fields including control systems, robotics, and signal processing. Introduction to tensor networks. Tensor networks are a mathematical framework used to represent and manipulate high-dimensional data. They are particularly useful for representing complex quantum states or large-scale physical systems. Tensor networks provide a compact and efficient way to describe the entanglement of structure of LTI systems. Challenges in applying Kalman filter to LTI systems. Traditional Kalman filters are not directly applicable to TI systems due to high dimensional nature. LTI systems often exhibit complex entanglement structures which are challenging to represent using traditional linear models. LTI systems often exhibit complex entanglement structures which are challenging to represent using traditional linear models. The tensor network Kalman filters overcome these challenges by leveraging the power of tensor networks. You can see the image, set initial values and predict state and error covariance, compute the Kalman gain, compute the state estimate, compute the error covariance. We move on to the next slide. Tensor network Kalman filters. Basics. The tensor network Kalman filter extends the traditional Kalman filter to work with tensor network representations. It represents the system's state as a tensor network, allowing for efficient representation and manipulation of high-dimensional states. By incorporating entanglement structure in the state estimation process, the tensor network Kalman filter provides more accurate estimates for LTI systems. You can see the measurements, three measurements: initialize system states, estimates, and system state for covariance. And second measurement is reinitialize system state estimate and system state error covariance. Predict state and system state error covariance to measurement time. Compute the Kalman gain and estimate system state and system state error covariance at measurement time. Tensor network Kalman filter algorithm. The tensor network Kalman filter follows a similar recursive adaptive process as the traditional Kalman filter. It consists of two main steps: prediction and update. The prediction step uses the current state estimate and the system dynamics to predict the next state. Tensor network Kalman filter algorithm conditions. The update step incorporates measurements into the state estimation process. It uses the predicted state and the measurement data to update the state estimate. The algorithm iterates between prediction and update steps to refine the state estimate over time. Advantages of tensor network Kalman filter for TI systems. The tensor network Kalman filter provides a more accurate state estimation for TI systems compared to traditional methods. It leverages the entanglement structure of LTI systems to capture complex correlations and interactions. The tensor network representation allows for efficient computations and reduces the computational complexity of state estimation. We can see the input and output state estimations, like zk is a input measurement and x, x cap and k is output state estimation. Set initial values x naught comma p naught, predict state and error covariance. X inverse k equals to f of x inverse k minus 1, p inverse k equals to ap k minus 1 a of t plus q. Compute the Kalman gain. K, capital K to the base k equals to p inverse k h power 7 into h p inverse k h power t plus r to the whole to the power minus 1. Compute the state estimate. X to the x cap k equals to x inverse k plus capital K to the base small k of z k minus h of x inverse k. Compute the error covariance. P k equals to p inverse k minus capital K k h p inverse k. We move on to the next slide. Applications of tensor network Kalman filter in LTI systems. Tensor network Kalman filter has various applications in TI systems, including quantum, state estimation, and quantum control. It can be used to estimate the state of quantum system based on noisy measurements. The tensor network Kalman filter is also useful in optimizing control strategies for complex physical systems. And again, you can see the Kalman filter algorithms of battery model, the right side of the page. Then move on to the next slide. Quantum state estimation using tensor network Kalman filter. Quantum state estimation is a crucial task in quantum information processing. Tensor network Kalman filter provides a powerful tool for estimating the state of quantum systems based on noisy measurements. It can handle high-dimensional and entangled quantum states efficiently. Quantum control using tensor network Kalman filter. Tensor network Kalman filter can be used to optimize control strategies for Quantum systems. By incorporating the entanglement structure, it can identify optimal control sequences for achieving desired quantum operations. Quantum control using tensor network Kalman filter has applications in quantum computing, quantum sensing, and quantum communication. Challenges and future directions. Despite its advantages, tensor network Kalman filter still faces challenges in scaling up to larger and more complex LTE systems. Developing efficient and scalable algorithms for tensor network Kalman filter is an active area of research. Future directions including exploring applications in other fields beyond quantum systems, such as complex physical systems and machine learning. Conclusion: we can conclude that the tensor network Kalman filter is a powerful tool for state estimations in LTR systems. It leverages the entanglement structure of TR systems and provides accurate estimates based on noisy measurements. The tensor network Kalman filter has applications in quantum state estimation, quantum control, and beyond. Thank you.